and do protein synthesis. So you might have heard the breakthrough that happened in AlphaFold from DeepMind, where they were able to take the same kind of sequence modeling idea and then apply it to protein. So what this kind of allows you to do is think of the ideas that you've learned so far and then try to apply it in different domains. So this was one of the biggest breakthrough in the medical industry when you actually applied this kind of idea to other places. Now, today we will specifically look at how do you actually kind of apply the ideas that you have learned in terms of language to more than language, right? So essentially, if you have, these are some examples of what is feasible today. Here is a prompt to Google Gemini model where we have a mix of text and images. So we have a kind of a science question, and then there is a student has put in some charts over there, and the model is able to now understand combination of this text and then human drawn pictures, and then provide a response. The same way for that was understanding. Now, same way for a generation, where from a natural language generation, things like ChatGPT, now you can generate multimodal output. So essentially, you have like, you can have an output coming out of your AI model that is a combination of text and image. So for example, if you give a picture like this of a picture, and then given this picture, what is the image? Can you kind of make it into emojis, right? So you get set of icons here. So being able to generate multimodal content is similar to how you generate how ChatGPT generates language. You can actually generate multimodal content as well. So you might have seen this popular thing where you give text input to the AI model and you kind of generate an image. Now, this idea can be kind of turned, and then if you build an AI model that can take it, for example, other forms of data, you can actually do some very interesting things. For example, in the area of drug design, where people, some of the researchers have been able to kind of synthesize novel proteins just by the same idea of text to image synthesis, text to protein synthesis, where you basically say, I want to create a protein which looks like this. And then, you actually create a sequence of, because these are sequence of, think of the proteins as a sequence of genes and then kind of amino acids. So you can actually synthesize and create new things like this. Here is another way, kind of thing. Here we have an input, which is a video, and then you ask a question on this video, and then the AI model is able to find answers for you from this video. Similarly, you can have image and then audio. So here you have a combination of an image and then an audio clip where there's some instructions about it, and then the model is able to generate some interesting response to that. So, and then you can have, for example, you can have, and here in the prompt, you have text as well as the screenshot of what the software outputted. Like, for example, here you have a screenshot where there are like 4 charts that were created by this code. And then you are now saying, okay, kind of you want to bring the last chart to the front and things like that. So you want to kind of correct the sequence of charts. So you basically tell the AI model, can you generate a code that will rewrite this application so that the code, the chart comes in a different way. So if you look at from this angle, there's a new era of kind of software that you can dynamically customize just by speaking to it. So imagine you have like you downloaded Microsoft PowerPoint or any software, and then you simply say to the software, hey, I want this icon, or like I want this to be happening like this when I press this button, and then the code automatically gets generated on the fly and then gets recompiled, and then you have a new software on the fly. So personalizing software on the fly. Same way, if we take the same idea, instead of screenshots, we have real images and some instruction that you speak to a robot, then let's look at some of the possibilities, right? So here, like for example, here you have a language model, and then you have kind of picture. This could be a real picture of robo manipulating something on your house, and then you are kind of wanting to instruct the robot to do certain things. You are basically directing the robot by speaking to it. So can we have a language model that would take in your question? If you say, "Hey robot, go pick up that yellow box and then come over here," can it understand? And then can these is like how we could generate code, can we actually generate code to even control these robots, right? So this was the other experiment that was researchers are doing. So how do you actually do it, right? So what would the input? Now, the language models take in text as the input, but now you have an image as well, or some kind of non-textual format as input. So how do you actually kind of bring that in to your AI model, right? So you basically have to kind of have some kind of intermediate encoder that kind of takes in the new image modality or new model, right? The new modality, be it protein image or robo, instructions, source code, whatever be it. You have to have some way to take that and then plug it inside the current input that the LLM is taking. So that's an encoder. So this encoder basically would kind of extract the visual meaning and then translate into a moral language kind of a meaning. And then you can have the generation, language generation, or code generation, which goes and controls the system again. So the encoder is one of the key pieces. If you just add that to a language model, then you open up to new possibilities. So you can have like screen images, the set of previous code that was fed into the robo, and then you can have this instruction, this language model instruct the robot to move in a certain way. Um, so from there, we kind of now see the architecture of how this could be done. Like, so for example, here you might have already you might have already been coding with language models. Now here we have, in addition to language, there are two inputs. So we have a text which says, given this image, and then you have an image. There is a photo of the robo in the real room, or here it's a virtual screenshot. So given this image, so you have both image and the text as the input. Then you have an encoder that would take this image and then embed it in a way that the language model can understand. And then the language model anyway is proficient in generating text output. So essentially now you can have something like this, where you have a real robot. So, and you're saying, "Hey, robot, go get the green chips for me," right? So, given that, so then the AI model, what's the input to the AI model? You have a photograph from the camera coming in. So, given this photograph, given this image, which actually goes into via the encoder to the language model, and then you say, "Go get me the green box," right? So what comes out from the language model is again set of instructions or the source code that would go and operate the this robot. So you can go actually and go check out the Google DeepMind research of this video demo. They have a video of this robot of the head of Google DeepMind research playing with this robot. So you simply by speaking to it. So this is how underlying it works. You basically take a photograph and then the human instruction, and then the language model generates next set of instructions to control the robot. And so here in saying sort these blocks by color. So then you're telling the robot to pick up these yellow boxes and put it in one corner, right? You're sorting it by color, right? What happens is and so the input is the instruction that you gave, and then it takes a photograph from the camera. Then you basically have instructions coming out from this. So it's a language model. So it will basically generate instructions. And these instructions go to another AI model that will convert this instruction to source code, feed it to the robo, and then the robo moves, right? And then the camera clicks again, and so it's in a continuous loop. So you basically can have a simply by speaking to the AI model, you are basically dynamically controlling the robot just by speaking to it, right? So this is how you can basically take your idea that you've learned around language models, right, in the NLP, and then suddenly you have using the same knowledge that you had in NLP to actually now do something in robotics, right? Amazing. Is that amazing that you take your current knowledge and simply by flipping it in a different way, you now have built a very interesting robot, right? Which uses the same idea that you've all learned, right? In terms of language modeling and NLP. And then you had now built a robotics application. So this is how you can basically use multimodality. So let's take a slightly more deeper look at the architecture and some few demos and some source code as well. So here we have image, text, video, audio, right? So these are typical four modalities. You can have more modalities. Um, it could be your heartbeat, it could be your um, CT scan, or it could be stock market forecast, or it could be some drug molecule like in your chemistry, whichever, like you can have different modalities. Now, if you take all these modalities and simply kind of feed that into a language model through an encoder so that you basically convert from the image modality to the language modality, or from the stock market trend to something that is more meaningful for the language model to understand, then you can feed it to the language model. And so if you take this input sequence here, like a picture, given this picture, you have a sequence of image and text together. Now, if you feed this in to a language model, which essentially nowadays are all transformers, and some of the newer architectures also use mixture of experts. So the transformer, I hope everybody kind of understands what's a transformer, right? You might have been a little working with transformers. Um, so, um, so you basically take these inputs into transformer, and then you can have, like you had the encoder, you now need to have a decoder, which will take the text which is coming out from the transformer, and then it will convert from the text back into image, right? Or back into protein sequence, or back into some visual content. So these are decoders which can actually transform back into the original modality. So that's how you were able to do this. Now let's little bit understand a little more details, the modality and the architecture, right? So given um, the same idea holds good, right? So initially you had a language model which takes in text in and then text out comes, right? Chat GPT does all this. BERT does this. GPT-2 does this, right? Where you have a language model, an AI model that takes input is the text, and then output is a prediction in terms of if it's a BERT, or in a GPT, you actually generate text. Now, all you're doing is you want to also feed in an image. You plug in an encoder, which will kind of take this image and then somehow feed that inside the language model. And then again, it can still reason, and then you can have text out. But if you want to have more a modality that is outputted, then you can have a decoder that will convert it back from the language embedding to the image embedding or whatever. So let's now quickly take a look at, as the world, all the research is switching towards how do we kind of get to the AGI, the general intelligence, how do we make it human-like intelligence, right? In that context, multimodality, like, taking whatever knowledge you have gained so far in NLP course so far, and then how do you actually add it and then make it much better, right? So, so why does multimodality matter? So simply because the world is simply multimodal, right? You have sound, you have image, you have video, you have stereoscopic vision. Basically, you have eyes which looks in stereo, that is 3D vision. You have touch, you have smell, you have different sensors, you have source code, you have graphical representations of like flowcharts. Those are graphical data, or like your binary search tree. This data structure which is in a graphical linked list, right? So you have all these data structures which are in graphical format. There is time series data. There is audio spectrograms. So far, ChatGPT 3.5, if it has been able to learn from simply from language that's across the web, right? So all the entire web, it's able to use that as a data set and learn. How about there's a bunch of huge content in YouTube, right? That's video as well. And there is also audio because the speech is there. So that's essentially a language. And so there's video content. So if you can actually now learn from the YouTube content, there's billions and billions of YouTube video on the YouTube system. So if we can train on that, then you can actually have a train on real world data sets, right? And so what that happens is essentially you will now be able to, while in 2023, researchers were looking at how do we actually create a language model that kind of the data set is essentially all the textbooks, all the Wikipedia content across the web. So you basically crawl the web and then you can create these language models. That's the data set for you. Now, in this case of multimodality, you have, for example, if you're having YouTube as your data set, then all the videos you can feed it in, and then you can create a language multimodal model that can understand YouTube video, right? And the text, which is essentially the audio there. So if you look at how deep learning and the area of now is popularly called the large scale deep learning or generative AI, the fundamental three principles have been the same, right? This same kind of idea that has been there for now since 2014 when neural networks got like the traction. So since then, it's the same idea, right? You basically take a neural network, you do back propagation, which essentially nowadays is done like in simple one-line code model.fit, and then there is the underlying framework that the library that will do the training for you. All the back propagation happens. But from your side, you basically are taking some data set, feeding into the AI model. You're building a neural network which can be different sizes. So the model size, you can construct a neural network that's bigger in size, feed in a lot more data, and then you basically have more intelligent machines coming. And so now we are at a stage where we have exploited all the text data in the globe, right? All the internet text information, Wikipedia content, all the textbooks, which can be fed into a GPT-3. Now we are at a point where you still can increase the data, and that's why you actually moving to multimodal. That certainly allows you to build this simply even more intelligent AI models, and that's what you're seeing in this recent thing. So let's check out some demos of what we can do with this. Just let me know if in the next there's a video of demo that I'll play. Just let me know if the audio from the video is coming out. In case it's not coming, I'll kind of reshare this.
The science experiment.
You are given 2 videos. Your task to learn the science concept from a teacher's demonstration and then analyze the student's experiment and then mentor the student.
Here's the analysis of the two videos. The science concept being taught by the teacher was Newton's third law of motion. The students performed two experiments. The students seemed to understand the science concept. Well done, everyone. You've all done a fantastic job demonstrating Newton's third law with these experiments.
Further, to scale to millions of children in developing economies, we need to address affordability challenge, so we design an AI solution architecture for affordable access.
So what you're seeing now is you had this video, right, of a teacher, right? So this is the first input. So the input was this video was the first input. Then you are basically feeding in the second input, which is essentially the kids here doing a similar science experiment. And then now you are letting the multimodal large language model to actually look at both these videos and then understand the science concept from the first and then coach the students in the second scenario, right? So essentially what you're seeing is the AI model is able to interestingly perform this very reasonably, very similar to how a human would have taken a look at all these videos and then so it's able to immediately get, okay, you're learning Newton's third law and, action reaction, and then what the teacher was doing, and then what the students were doing, they were basically doing these two experiments, the balloon powered car, which is the same idea of action reaction. And it says the students seem to understand the science concept correctly. They are able to recognize the air escaping from the balloon, which is action, cause the car to move, which is the reaction. So interestingly, what you're seeing is the AI model now suddenly is able to now do something very interesting, right? You basically have learning that happens in a different level with this kind of coach that can so here, what was the input, right? So essentially, you had video from the teacher, video from the student, both going in, and then you had some interesting AI model that does this interesting thing and then guides the student, right? So it kind of identifies where the gap was in case the student missed some idea. Then, so let's take a look at how do you actually code this, right? So do you think coding something like this will be quite hard or easy? Okay, so we'll get to the code in a few minutes. So you can basically now take this is called chaining of different AI models. So what we are doing is we've taken three videos in the next demo. We have taken three videos of somebody treating, doctor treating patient one, then a similar scenario, another doctor in another city treating a similar wound in another hospital, and then we have taken a third similar, right? Similar another third doctor. Now you're basically telling the multimodal model to basically watch the video, understand what they're doing, and right based on all the understanding from all the three experts, all the three doctors, can you come out with a general idea of what they're all doing, what is the best practice that the doctors are doing, right? And so you're basically trying to learn from the experiences. All humans, we have all gained wisdom by observing and learning from experience. Now you're taking an AI model to learn from the experiences of 3 different or like 10 different doctors on a particular, how to treat a particular medical emergency scenario. And then these experiences from 3 different doctors, you are basically extracting, and then you're feeding it to the second stage of multimodal model where all these inputs go into the second stage, and you're now saying this to the second stage model that now this is the input from doctor one, input from doctor two. Input essentially how the doctor performed that surgery or perform this treatment, right? You take all this input and then learn from the best ideas from all these 10 doctors, right? And then give you and then output a kind of a best practice, right? So you're saying learning from the wisdom of multiple people, experience of multiple people. And that's what you're doing here. And then once you have the idea extracted, then the best practice is extracted. So the extracted output could be a text output. It could be also with the image generation. You can have kind of animated or like, clip arts generated on how to treat such scenarios. And then now you can actually deploy it in field, right? Where you have similar junior doctors or junior paramedic going in somewhere. And then you can feed the best practice that you will learn from all the 10 doctors. And then when the actual junior doctor is performing, then you actually can guide the person, right? You can actually check if the junior doctor is performing as per the best practices that all the experts are following. If not, then which part of the surgery or medical procedure they are missing, and then how do you actually coach? So let's take a look at a demo.
Sustainable Development Target 3.6. How do we reduce deaths post-accidents? Every year, around 5 million people die to severe bleeding after road accidents. Many deaths can be prevented by timely first aid procedure by any citizen. If you see a person severely bleeding, you need to do something to save a life. This is because the person may bleed out before the ambulance arrives.
Do something. What to do? How to do? Here we design an innovative solution to enable citizens to save lives with the wisdom of the paramedics. In this paper, we create an AI solution. We investigate this. What can transfer the wisdom of the experts to the citizens? Can the AI gather best practices by observing multiple paramedical experts? Can this knowledge be generalized and transferred? If the AI encounters new scenarios, can it still provide guidance to citizens? By acquiring the know-how adopted by paramedical experts, the multimodal AI can analyze if I am doing the correct procedure of first aid, and then guide me based on the wisdom of the experts. To find answers to these questions, we design an interesting approach. Firstly, the idea is to learn the wisdom by observing many procedures practiced by different paramedics. Note the input is video of the medical procedure combined with text description. Second, the AI learns the general best practice by observing multiple paramedical experts in different scenarios. Thirdly, the citizen is guided based on the learned paramedical wisdom. Hence, the citizen can control severe bleeding and thus prevent the person from bleeding to death.
Your task is to understand the ideas from the expert and then analyze and guide the student's performance. Based on your understanding of this situation and the steps taken to reach an objective, could you synthesize an abstraction of how to handle similar situations?
First, make sure it is safe for you to help the injured person. Move the person to safety if you can. Wear gloves and try to stop or control the bleeding until help arrives. Apply steady, direct pressure to the bleeding site with a clean cloth, gauze, or tissue until the bleeding stops. Don't remove the cloth, even if the blood soaks through. If it does soak through, wrap or compress with more bandages and keep the constant direct pressure.
Based on the abstraction you created above, think systematically how an expert will handle this new situation. Did the student handle the situation correctly?
So what we are doing is actually having the AI model learn from an expert, and then now this is the student or this is the real scenario, and then the AI model is having the best practice. Now it's going to coach or observe the junior doctor on this new accident spot, and then kind of intervene if So it's also watching, right? You have turned on your smartphone camera, and the AI model has the best practices that it's picked up from the how the experts handle similar scenario, and then it's going to see if you are doing the same way. In case you are missing certain steps, like as per the guidelines, they have they kind of put down the guidelines on what to do in kind of severe bleeding to stop the bleed, and so it's going to
A. What was the situation? The student is in a situation where a person is injured and bleeding. B. Did the student handle the situation correctly? The student.
So what you're seeing is the model has identified these 4 steps, the sequence of activities that was performed by the expert. First step was ensuring the safety of the environment if it's an accident spot. So there are broken glasses and things like that. So that basic idea. Second is calling for help. You call some phone number for help. And more importantly, stopping the bleeding, right, by applying pressure and then cleaning the wound. So those are the 4 steps it has identified as best practices for similar scenarios, right? You ensure the place is safe, they call for help, then you try and arrest the bleeding by applying pressure. And so then you can kind of let the understanding and how the person actually pat the bandage and how is able to perform it right now, right? So let's take a look at how. Do you think this code for this will be quite complex or easy? So let's take a look at how is the coding here. We simply have some pip installs happening, and then we basically import some libraries here, right? And then we invoke a multimodal model, Google Gemini model. And then here you see the input, how we are passing the input. Video 1, video 2, text 1. And so this is very similar to how we saw in the things like that, right? Image, given this image, things like that, right? So you basically have sequence of text, video, and then text followed by text, videos, text, and which is the same kind of architecture here that we initially started with in terms of having the input in terms of text and image together. So you have that text, video, and then text combined together. So you basically giving a reference to the video that is in the cloud, the URL for the video where you posted it, uploaded the video. Then the text prompt that you're giving, right? So there are 2 videos. Check out the first video, and based on based on how the expert did, guide the second person, right? So you basically are kind of instructing the language model to, or the multimodal language model to kind of, you are providing the instruction to learn from the first and then advise the, so this is all it is. So you basically have very simple code. You put some safety settings so that the generation is safe, and then you are done. So that's all it is. Now the system is just running. So isn't that cool? So you have like 5 lines of code which did the entire demo there and saving millions of life. Okay, last 10 minutes on how do we kind of
sustainable development.
Okay, so you kind of saw this idea. So the basic idea here seems to be that you have a language model, and you're basically adding a multimodal input by stacking an encoder, and then for the generation you're stacking an decoder to the language model both in the outside in the output side. Same idea. So basically, this is the broad idea, right? You have LLM, you have text going to the LLM and text coming out from the LLM. Now you have new modalities, image, audio, video. You have an encoder, and then you have a connector. There's something called connector that you have to host. Connector again is encoder is again a neural network. Connector is again another neural network, and then um, you have the decoder. So what's a connector, right? It has to connect the image modality to the text modality. So it's again a neural network. You put in a bunch of layers over there, and then it learns to connect the alignment between image and audio, like image and text. So let's see how this has evolved over the years. 2015, Andrew Karpathy, who is right now was Stanford student, Dr. Fifi Lee, he went and created this breakthrough show and tell, right, where you had initially at RNN LSTMs, which took in, text out, right, standard stuff. What he did was he now introduced, can we feed in an image into the LSTM, right? So you put an encoder could be simply an CNN or a VGG or a ResNet, whatever it is. So you basically took a VGG or like a ResNet, you stack it on top on the front side of the RNN network. And then the last layer of the ResNet, you basically take it and feed it inside into the LSTM as an input. Now, what happens suddenly is you are now able to create an image. You are able to feed image to an RNN model by transforming that image by an encoder. Encoder here is simply an image classification neural network, except the last layer which was stripped out. And so essentially, if you strip out the last layer of an image classifier, then you basically have features left. So you have the features that feeds that goes inside the RNN, and then so essentially you are basically transforming the image into image features, and then these features go inside the RNN. And so that's the basic idea, and then you now have the architecture defined. You basically collect a set of data set. Here the data set will be like, instead of image and the pictures, the description for these things. And the next time you pass an image, you get the description. So essentially, that's the whole idea. In 2021, so the only change that has happened was this time it was RNN and CNN. And by the time in 2018, transformers got introduced, and that became the state of art. Everybody liked the way transformers are able to scale for larger data, larger compute size. And so essentially you replace both these areas with both the encoder with transformer and the sequence model, which is the LSTM, to a transformer again. And essentially you got CLIP, which is the breakthrough in 2021, where you had a transformer going in the text encoder. You have another transformer which goes into the image, and then how they are able to train this. I think we should finish this in another 5 minutes from now. I think we are right on time. Yeah, another 10 minutes, 4:45, we should wind the class. Okay, so so how you are able to train this? How do you actually collect? So if you are building this clip yourself, how will you, what is the data set that you will create, right, to train this? So how will you get the data set? You take a textbook that textbook has a kind of a bunch of figures, and then below the figure you have a description. This is a figure which is about this, right? A photo of so and so, right? A picture explaining how Newton law works, right? So essentially, all figures have a caption below it, a photo of so and so, a photo of this. So that's essentially, if you can grab your hand, put your hand on this image and the caption below the image, then you essentially got your data set created. Now you take that as the data set, and then you feed into this AI model that you created, and then you're able to train it. And so that's all is the idea behind Clip. That's how you are able to do that. Now, since then, in 2024, this year, Google has kind of extended the same idea simply by scaling it to video. Right? You had a lot of research happening on image. Now, since you have access to YouTube content, if you're the researcher within Google, you take this, and then since you are all having YouTube content, and all YouTube content has some audio component along with it, which is the speech, people speaking in that. So you do speech recognition, and then you have the audio transcript, which is the language. So you have text, you have video, then you basically take it and then feed it in the same architecture, which is essentially the same idea that you bring in the video, extract the features from that using some image based neural network, and then you feed that inside the sequence model, which is here all transformers. And so essentially you have a set of transformer layers, and then you feed in the sequence, and then you are getting this idea. So the idea is simply you have a language model. Right now here, what you're seeing is you've all learned to do NLP, which is essentially feeding in text to an AI model, and the AI model creates a text out. All you're doing is now taking an image and then stacking it as though it's like you're basically taking a sequence of all the pixels over there, and then you're passing it to the model, and then you are able to now kind of take the same idea of NLP and then bring it to multimodal models. So then the question arises: should you actually think in language, or should you think in visual, right? Right. So some of you are like, you know, some humans think in, like, if you uh, asked to think or remember something, you have photographic memory. That means you're thinking in vision, in visual format. Some folks who are like more into music and like folks think in auditory format, right? You think as a sequence, right, one after the other, right? So, so how do you actually represent these content? You can, like how different humans think in either vision or in image or in language. You can do the same thing. So, and so that those are the two different ways to construct this AI model. You essentially have image-based binding or language-based binding, right? So essentially, 90% of today's multimodal models are essentially using language, but there is also, you can also build this with image as the fundamental embedding space, right? If you start with the GPT 3.5, then you're starting with language, and then you're adding an encoder to it. But if you're starting with an maybe a VGG, then you're starting with an image based model, and then you're stacking language to it. So you're essentially putting an encoder which will translate language into the image, and then you're building this thing. So you can do it either ways in different based on the situation that you can. But right now, most of the research has been happening on the language-based encoding, or the 10% of the image-based thing is also there. Now, once this is there, now from NLP, now you're looking at how do you do NLP in Tamil, right? Or in any language that you would think is more appropriate. If you want to build a language model for a new country, right? Or new dialect. There may not be enough data set that exist. And so that's the challenge. now with the advent of multimodality, you have image as a kind of a rescue path where like if since the AI model is learning from image as well, then you can bring in that aspect to kind of mitigate the risk on low data set from other languages. And so you, just to summarize, you had earlier language models, which is text in, text out. Now you have encoder that will convert any other modality, could be image, and then it could be generating image out. But it necessarily need not be necessarily image. You can think of, instead of image, you feed in something else, right? Maybe you feed in a chemistry molecule, right? A chemical, like all of you have learned some organic chemistry molecules. So if you feed in that, right, you should be able to now generate new molecules, new structures, right? New geometries, new organic molecules, like that. So that's how you basically invent new molecules, and you can now say, okay, hey, generate me a molecule which is a mix of carbon plus this, and then you get a new molecule structure defined by a language model. And so you can extend this idea to different modalities. Like you can take in any text and then you can put in a satellite image and then you can kind of do something together, right? So you can kind of take this idea and extend it. So the final concept here is in terms of few shot learning, where essentially here the idea is to kind of train or like, soft train the AI model by giving few examples, right? For example, here is a person with cerebral palsy, autism, and so when these children speak, it's very difficult to understand because the way they pronounce the language is very different. And so so you basically what you can do is, as a mother, the mother is able to understand how the child is speaking. And so you have the audio visual of the child and then the mother's actual interpretation. That is an example. That serves as an example. And then you use the example for the next time the child is out, you can basically have the AI model go and do that, right? So let's take a look at how quickly, last 1 minute, the demo of study source code around this, where you have you install a bunch of libraries, you install the Gemini model, and then you have the few short examples. That is, this is the video of the kid, and that's what the child is said in that video. If the mother has typed out that, and the next video where the child is actually you want to find out what the child said in the second video, second clip, right? Outdoors, and then the model is able to learn from the few short examples provided earlier, and then come out with this. So that's that's how you kind of able to use some of these models. So to sum up, we had today looked at your NLP knowledge. How do you scale that to basically design next generation AI systems, human-like, the trend towards AGI, human-like performance. And you can basically think of this as a sequence modeling problem, and then bring in any sequence, and you basically kind of combine multiple sequences together in an architecture, which is essentially you're stacking different sequences through an encoder, and then bringing everything into same modality. The modality can be, so the embedding can be in, you can think in image or think in language, right? So instead of large language model, large image model, if you build it that way, if you start with the image model and then you plug in an encoder, you can do the other way around as well. So you can either be thinking in image or you can thinking be in language, right? So both ways have been proven to be possible. While mostly people today are thinking in language, and then stacking in encoders from image, which will actually come back, put the embedding back into language modality. You can also do the other way around. And so that's the kind of the core architecture. You learn this core architecture of how do you basically take your knowledge of NLP, and then you stack in multimodal input. Then you looked at why this is going to be powerful. Why this is going to be powerful, because the natural data is more powerful, more diverse than language. And then there is a scaling law of all the deep neural networks, that the more the data you have, the more the model size is, the more intelligent the system behaves. Right. So essentially, you now have we ran out of data for the GPT-3 time frame, where all the web was already crawled and the models got intelligent. But then to further increase the intelligence, you needed more data, and then the data is now, for example, available in, say, multimodal format, YouTube content, or real world feeds. And so you basically start looking at how do you build more intelligent models by increasing the amount of data set that you can feed in. And that led you to kind of do very interesting things. We saw some examples of video question answering, we saw a demo of how the AI model was able to understand from different experts by just observing videos of different experts applying that bandage, and the way they kind of applied the bandage one, right, to different, and the way they applied the pressure to stop the bleeding. And it's able to distill all that and then combine the learning from different experts and then bring it together. And then finally coach a junior doctor. So essentially, you're now trending towards human level AI performance, simply by this kind of simple idea of transforming all the knowledge that you had and then stacking in multiple modalities. And then you're stacking now different layers on top of each other, different, like this LLM chaining. So you had stage 1, stage 2, stage 3, things like that. I guess this still remains the basic idea that was invented in the paper Show and Tell, where you basically took an image and then extracted image features, put it into an RNN. Nowadays, people are doing instead of RNN and the CNN, you basically replace these two layers with transformers, and that's what has been there in CLIP, which was the vision text modality, and in Gemini, it's the video text modality. And it's the same idea that you basically think of the input as a sequence, and then you are able to now do this. So, and now you are able to now even do further than you can create something new on your own, not just be limited to what's happening today, but you can actually think of feeding in something new, right? Something more interesting, maybe climate data or like stock data along with market trends, and predict which will be the next stock that's going to go up or down, or based on market conditions. Or you feed in drug designs, and you feed in like all the electronic patient records and see which drug was able to perform effectively in which type of patients, things like that. So kind of the possibilities is endless. And these models are now also able to learn with few examples on the fly. And that's the few short themes. So, and then you saw the source code, how easy and effective you can build some of these systems. Thank you, all the very best.
Thank you, sir. Rajagopal sir,
Thank you.
thanks a lot for sharing your NLP insights for real-time applications, especially for this paramedical application, sir. And you explained lovely multimodal applications with interesting videos and your interesting slides, sir. Thanks a lot. Thank you for sharing this knowledge with us. Thanks a lot, sir.
Yeah, thank you so much.
Okay, sir.
Thank you so much, all the students. Thanks, madam.
Okay, sir. Okay, now we can. Students, do you have any questions? Okay, then we'll wind up the section. Thank you, sir.
Thanks a lot, ma'am.